Shanghai should not legally exist. Right now, a colossal weight is pushing down on the Earth. The Shanghai Tower alone weighs 850,000 metric tons. Beside it sit two more massive megatall skyscrapers, forming the most vertically dense cluster on Earth. But underneath the glittering glass lies a geological nightmare. Shanghai is not built on solid rock. It is built directly on a deep, waterlogged river delta where the soil is basically a giant underground mud sponge. If you build a heavy structure here, the ground will punish you. Gravity forces the water out of the mud, causing the soil to collapse and sink. Between 1921 and 1965, groundwater pumping caused a catastrophe, and the center of Shanghai literally sank by 8.5 feet. Western engineers confidently stated that building super tall skyscrapers here was impossible. Yet, these three megatowers stand perfectly still, defying gravity through a series of physics miracles that begin deep inside the mud. To understand the danger, we must look to soil mechanics and a fundamental civil engineering formula known as Tezagi's effective stress principle. This principle dictates that soil grains and water share the structural weight, meaning total weight equals effective soil stress plus pore water pressure. When you drop an 850,000-ton tower onto the ground, pressure spikes deep below the surface within a layer known as Layer 4 mucky clay. This specific clay features a natural water content of up to 45%. Under extreme pressure, it changes its physical state, shifting from a solid plastic into a treacherous, semi-liquid hazard. As water is violently squeezed out of the clay matrix, the entire soil skeleton compacts, triggering severe and uneven land subsidence. If a skyscraper settles unevenly, it creates a fatal structural flaw. The building begins to tilt. This movement unleashes a destructive force called negative skin friction, where the settling clay grips the foundation columns and actively drags them downward. This downward drag can snap concrete anchors completely, and a single failure means a multi-billion-dollar collapse. To stop this, Chinese engineers had to invent a giant underground clamp. Because solid bedrock sits a staggering 200 meters deep, the building's columns could not realistically reach it. Engineers could not anchor the towers to solid stone. Instead, they turned the soft river mud into their greatest asset. Beneath the Shanghai Tower, workers drove 980 friction piles deep into the earth. Each pile is a cast-in-place concrete column measuring 1 meter in diameter that plunges 56 meters into the ground. Remarkably, these piles do not rest on anything solid. Instead, they rely entirely on the rough surface area of their shafts. The thick, high-density clay grips these concrete shafts like a vice, creating enough friction to completely cancel out gravity. To tie these 980 teeth together, they required a massive unifying mat. Workers excavated a giant basement hole 31 meters deep and executed a legendary 63-hour continuous concrete pour. A fleet of 450 trucks poured 61,000 cubic meters of concrete to create a solid foundation raft 20 feet thick. However, massive concrete pours face a chemical enemy known as hydration heat, an exothermic reaction from cement mixing that generates extreme internal heat. If the inside gets too hot while the outside cools, the raft will crack and fail. To bypass this, engineers formulated a unique triple blend cement, mixing standard cement with fly ash and blast furnace slag. This slowed the chemical reaction, keeping the mix cool and durable without the need for complex internal cooling pipes. The subterranean matrix was locked, but a new enemy was waiting in the clouds. At heights over 1,500 feet, gravity ceases to be the primary threat. The true king of destruction is lateral wind shear. Shanghai sits directly in a violent typhoon belt, where Category 5 storms regularly hammer the financial district. When high-speed wind hits a flat, square building, physics attacks. The air separates at the sharp corners and forms alternating, low-pressure whirlpools. This aerodynamic phenomenon is called a von Karman vortex street. These vortices shed at a dangerous rhythmic frequency, and if that shedding frequency happens to match the building's natural frequency, a phenomenon called a lock-in occurs. The tower will begin to sway violently from side to side, causing severe structural fatigue and eventually snapping the concrete core. The neighboring Shanghai World Financial Center utilized a brutal, effective fix to combat this. They cut a massive 50-meter trapezoidal hole directly through its summit, giving it the iconic look of a giant bottle opener. High-altitude wind flows directly through this aperture, equalizing the pressure and slashing lateral drag forces, which ironically turned out to be both cheaper and easier to build. Yet, the final tower in the cluster would take aerodynamic warfare to an entirely different level. For the main Shanghai Tower, engineers traveled to a specialized wind tunnel in Canada to test dozens of scale models against artificial typhoons. The data was clear. Standard building shapes would catastrophically fail in a major storm. Their solution was a continuous asymmetrical 120-degree twist that spirals perfectly from the base to the peak. This twisting geometry acts as an aerodynamic camouflage, forcing the wind to disrupt itself as it scales the glass facade. Because the air is constantly disrupted, low-pressure vortexes can never synchronize against the structure. This single, brilliant design choice slashed lateral wind loads by a massive 24%. That math fundamentally altered the economics of the entire project. Because the wind loads were drastically lower, the building required far less structural reinforcement, saving 58,000 tons of heavy structural steel and $58 million in cash. It also made the tower significantly lighter on its soft soil foundation. But even with a perfect shape, a tower this size still sways. To keep the top floors habitable, they needed a mechanical heart. Even with a perfect spiral twist, a 2,000-foot giant will inherently flex. The upper floors of the Shanghai Tower can still sway up to 3 feet during severe typhoons, a movement that causes immediate motion sickness for the people working inside. Deep inside the 125th floor sits a monster. To guarantee total comfort, engineers built a colossal mechanical heart deep inside the 125th floor, a massive 1,000-ton tuned mass damper. This 2.2 million pound steel weight hangs from thick cables and stands as the largest stabilization pendulum ever constructed by humans. When a typhoon wind pushes the top of the tower to the left, inertia takes over. The heavy steel mass resists the sudden movement, lags behind, and swings powerfully in the opposite direction to the right. This countermotion applies a massive restoring force to the concrete core, acting like a giant anchor pulling the top of the building backward and reducing lateral acceleration by 60%. Traditional building dampers rely on large hydraulic pistons filled with oil, forcing fluid through small valves to slow the sway. But hydraulic systems face a major mechanical limitation called stiction, static friction, meaning the piston requires a massive initial force just to start moving. This means during minor storms, a hydraulic damper does absolutely nothing, leaving the tower to swing unchecked until the wind force gets large enough. Furthermore, hydraulic systems utilize high-pressure rubber seals that inevitably degrade and leak over time, and a fluid leak at 2,000 feet could trigger a catastrophic maintenance shutdown. The Shanghai Tower required a system with zero physical wear parts. To solve the wear problem, China installed an advanced electromagnetic shield, the world's first megatall eddy current damping system. A massive copper plate measuring over 1,000 square feet is bolted directly to the bottom of the shifting pendulum. Mounted on the floor directly underneath this plate is a permanent grid containing 125 high-power neodymium magnets. A precise, calculated air gap separates the two systems, ensuring they never physically touch throughout their entire range of motion. When the wind sways the tower, the copper plate slides across the magnetic grid, triggering the fundamental laws of classical physics. According to Faraday's law, the moving copper cuts through the magnetic fields, inducing a powerful electrical voltage inside the plate. This voltage generates swirling loops of electricity known as eddy currents. Then, Lenz's law takes over the mechanical loop. The eddy currents generate their own secondary magnetic fields inside the copper that directly oppose the permanent magnets below them. This interaction creates a powerful, invisible magnetic braking force that effortlessly slows the 2.2 million-pound pendulum without a single watt of friction. The kinetic energy of the typhoon sway is seamlessly converted into low, harmless heat because there is no solid friction, there is no stiction threshold. The system responds to the tiniest vibrations from minor winds instantly. With no high-pressure fluid seals to leak or replace, it is a flawless, self-regulating shield powered completely by the laws of nature. The Lujiazui Skyline is far more than an engineering achievement. It tracks a massive, historic shift in global political power. In 1999, the Jinmao Tower was completed, but it was designed entirely by an American architectural firm based in Chicago. At the time, China had to import the high-strength specialty steel pieces because they lacked the domestic software required to model complex composite outrigger trusses. By 2008, the World Financial Center represented a joint international partnership. Foreign engineers handled the complex calculations, while local Chinese crews executed the physical building. Then came the Shanghai Tower in 2015. This megatall marvel represents total domestic engineering autonomy. The rigorous verification and technical execution were led entirely by Shanghai's Tongji University. Local scientists independently formulated the high-performance C60 self-compacting concrete, utilizing local industrial byproducts like fly ash and slag powder. Main domestic contractors developed a proprietary, self-climbing hydraulic slip-form system to cast the concrete core floor by floor with automated digital precision. Through this single skyline, China transitioned from a technology importer to an aerospace and civil engineering hegemon, proving they can successfully build a vertical city anywhere on Earth. The three towers of Lujiazui stand as monuments to human execution. Together, they have successfully transformed a waterlogged alluvial swamp into a hyperdense economic fortress. They defeated the soft-moving mud with deep friction matrices. They conquered Category 5 typhoons with aerodynamic twists and structural portals, and they tamed the destructive sway of the Earth using high-powered magnets. While Western experts originally claimed the local geology would reject the weight, China rewrote the rules of structural engineering, the impossible skyline is standing tall, and the laws of physics have officially been conquered. If you liked this video, then subscribe for more.